Hello. Let's see if my microphone's the correct one. Yes. Hello.
Yes, I can hear you.
I just couldn't hear you, so
Oh, sorry. I was muted.
somehow I was on the wrong speakers too. So there's a whole process of making sure the right microphone and the right speakers are set up. Feel free to just shout out if I start working something on the board and you're still looking at the slides that I'm sharing rather than at the board.
Okay.
Just let me know, because sometimes I forget and just start writing stuff and then you won't be able to see it. That hasn't been a big issue because nobody's been at home. So now I've got to really get good at it. Okay, let me just get a count here. 1, 4, 8, 12. Okay, so that agrees with the number I'm expecting to be here. Now, Himangi, I thought you said Anna Kate was supposed to be quarantined too. Was there someone else who was supposed to be quarantined with you? Because
No, I think it
no,
was just me. We were
just
just
you.
working
Okay.
on the presentation together, so it was just,
Oh, gotcha,
yeah.
gotcha. Okay. Then I am missing one person that I'm. Well, Noah, I know, is supposed to be gone. Blonde-haired guy. Jeremy. Okay, yeah, I'm not expecting Jeremy to be gone, but we'll see if he shows up. Okay. Well, as I said, I haven't even had a chance to start looking at the exams yet, and I will do it this weekend just so I can give them my full attention rather than trying to rush it. But my plan is to get them back to you Monday. I certainly don't want to let it linger too long, given how fast things are going this semester. But any other concerns before we get into chapter 5? So we were going to have a 5-minute presentation today, so that's going to be delayed, and the one tomorrow is going to be delayed as well. So I'm sure we'll have one coming up next week. So let's just, well, I'm going to do the usual thing and get into an abbreviated version of the slides. So let's see if I share screen. And let's just share screen. There he is. And go to slideshow. Okay. As you saw, some of this stuff can be rather confusing. It starts out rather simply and then can get a little bit complicated. And so we're going to work through a whole bunch of problem-solving problems that, again, are different than the ones that were covered in the video. Some of the video ones were rather complicated too, and we'll sort of flip through the solutions. Feel free to ask if you didn't understand something and you're still not understanding it as we sort of go through it. I'm going to try to stand over here and point with the laser pointer just so I get used to treating people who are viewing at home the same way. So I'm one of the virtues of having the videos and having you watch ahead of time is some things that are derivations that do take a fair amount of class time, and I'm not going to test you on, so you're not required to know this, and I'm just going to refer you to the video for the detailed explanation. I'm not sure how good of an explanation or detailed Giancoli did, but the idea is we're studying uniform circular motion. That means an object is going in a perfect circle, that's the circular motion part, and the uniform means the speed is the same. Velocity, of course, isn't the same. Velocity is changing all the way around, but the speed is the same. So that's uniform circular motion. And after much great effort, we were able to show that when an object is in uniform circular motion, it's, for example, here it's going around in a circle counterclockwise, and at this point over here, time t1, at that instant, its acceleration, well, its velocity is changing, it has an acceleration vector, and the acceleration points towards the circle's center. That's perhaps non-intuitive for most of us. So it's accelerating in this direction at that instant. And the magnitude of the acceleration depends on its speed, and it depends on the radius of the circle. The bigger the speed, the bigger the acceleration, and the smaller the radius of the circle, the greater the acceleration. So it's v squared over r. That is a formula you need to remember that's associated with uniform circular motion. This is acceleration just like any other acceleration, but for some strange historic reason, it gets a special name when you're in uniform circular motion, or we'll see it applies in a more general sense to non-uniform circular motion. People talk about this v squared over r, or the acceleration pointing to the center as centripetal acceleration. It's still just the acceleration. Centripetal, I think, means center seeking or something like that. It just means it's pointed towards the center. I really don't like that people use that term, but it's used all over, so we may as well get used to it. It's just the acceleration for this kind of motion. It's a vector. So as you're going around the circle, at every position, it points toward the center, and it has the same magnitude. If you're going around at the same speed, v is the same everywhere, and r is the same. You're on the same circle. So that v squared over r isn't changing, but the direction is changing as you go around. There was a first simple example in there involving, just to eliminate as many forces as possible. We've got an astronaut in deep space. There's no gravity around that's significant, no other kinds of forces, except that there's a mass attached to a string. And the astronaut, well, I'm not in deep space, so this isn't going to be a good example of it, but here's something we can imagine. I'm in deep space, and well, hopefully this string doesn't snap. I don't think it's the strongest string. But in this case, we can talk later about why this is an example of non-uniform circular motion by virtue of gravity acting. But if I were in deep space and I did this and kept the center, it's kind of hard because this is a pretty heavy mass, kept the center at the same location, it would just spin around at a constant speed and in a circle. So that would be an example. And so here's an astronaut spinning something at 80 revolutions per minute. That's RPM units that maybe you've heard before. That's a rotational rate. And the question is the ball accelerating? Well, yes, it's accelerating because its velocity vector is changing. And what's the magnitude of its acceleration? The direction of its acceleration is constantly changing. It's always toward the center of the circle, but the magnitude is not. And in order to calculate that, in this particular example, we're on a 0.7 meter radius circle that this ball is going around on. So we know r. The challenge is to calculate v, and this is one of the things that I did several times in the video, but it's worth detailing again. How to calculate that speed? It seems like it's related to this 80 RPM. The faster the RPM value, the more revolutions per minute you have, the faster you'll be going. But those aren't velocity or speed units, right? It's not a distance over time. It's number of revolutions per time. So the question is how to change that to a speed or use it to determine the speed. And the way I refer to it sometimes as the distance over time trick. It's not really a trick. It's just using the definition of distance over time. But in this case, for example, something is moving with constant speed. And anytime something is moving with constant speed, we can calculate its speed by using any distance as long as we use the corresponding amount of time that elapses in the denominator. Or we can choose any amount of time. And as long as we use the corresponding distance it moves in the numerator, we're okay. And so we're just going to choose either the distance or the time to make it convenient. Now in this case, because we're given some information about what happens in a minute or 60 seconds, it goes through 80 revolutions every minute, the convenient amount of time that I'm going to choose is 60 seconds or 1 minute. I'm just converting to SI units, so putting it in seconds. And the question we need to answer then is, how far does it travel? And the answer is, it goes through 80 circumferences of the circle, right? If there's 80 revolutions in every minute, the distance it moves is 82 pi r's. And so by using that that reasoning, I can figure out what the speed is. And in this case, it's not a very interesting number, from 5.8 meters per second, close to that. And then I can plug those numbers into the v squared over r formula and figure out what the acceleration magnitude is. And it's a substantial acceleration. We think of 9.8 as being pretty big acceleration, right? I mean, this thing's falling to the floor at a great acceleration rate, but this is quite a bit bigger than that, right? It's 5 times as big as that. And it's about, little g is about 10. This is close to 50, so it's about 5 times as big. So if you were on that string, you would feel some great, pulling effects from that force. You would feel a lot going on. And then one of the things that we can ask when we know something about that acceleration is, how does that tell us about the forces that are involved? And so in this particular example, the only force that if it weren't by virtue of the string, if the string weren't there, this thing would be going in a straight line. So the only reason it's going in a circle is because of the string force on the ball. It's the only force that's acting on the ball. And I can use F net equals ma, and we're going to be doing that over and over again in this chapter. But to do that, I need to draw a free body diagram. So here's my free body diagram up here. Here I'm saying at this instant, where it just happens to be at this position in the drawing, I'm going to draw a free body diagram. So I'm going to draw the ball adjacent to it. The only force acting on it is the tension from the string. So in this case, it's a very simple free body diagram. There's only one force acting on it. And our rule of thumb for how to put axes on a free body diagram is always, if you know the direction of the acceleration, always take one of your axes pointing in the direction of the known acceleration. And at least at this instant right here, for which I'm drawing this free body diagram, the direction of the acceleration is toward the center of the circle. It always is for uniform circular motion. So I'm going to choose one of my axes, I called it the plus x direction, to be toward the center of the circle. The other one could be tangent to the circle. We just didn't need it here. And when I do F net x equals max, of course, there's only one force, and it comes in with a plus sign, that t. And then the m times ax, well, the magnitude of a is 49.1. It's pointing towards the center of the circle, so the x component of it is 49.1 meters per second squared. So I can calculate, in this case, one of the forces, and we'll often do that, use F net equals ma to calculate a tension in a string or some other force that's acting. Okay, questions on that example before we do several problems? The first one's meant to be straightforward, and maybe you guys have seen this if you're a sci-fi fan, and people are traveling through space. One way they often generate artificial gravity as people are traveling maybe many years in space. Your body wouldn't do very well if you had zero gravity for that whole time. Your bones just basically decay away. So you need something to simulate gravity, and we have no way of just turning on gravity in the absence of a huge amount of mass, right? To make this amount of acceleration here, I need a big Earth underneath me, so we can't carry that along on a trip to another planet or something like that, or even farther. You're welcome. So here's how they do it, and this is a technique that really works. So let me go to the screen now. Maybe reorient this a little bit. The idea is you make your spaceship in the shape of kind of a tube, a very big tube. And then you have that tube rotating. Now it's rotating, but it's also traveling through space. But as it's traveling through space, it's rotating, sort of tumbling over itself. And if you ride along with it, it looks like it's just rotating in a pure circular motion. And there's no way to say that that's not true. That's an inertial reference frame. If you're just sort of riding along with it at constant velocity, it's executing uniform circular motion. In other words, every object inside of it is going in a circle. So I've got a picture of some person down here who's standing inside the tube where the air is, right? They've got a tube with the air inside there so you can breathe. And this thing's rotating, and the idea is as it rotates, this person is going in a circle. And if they go in a circle, they're accelerating at this instant toward the center of the circle. So this is what the person's acceleration vector looks like. And therefore, if a person's accelerating in that direction, there's got to be a force that's being applied to them along that direction. And if I look around, if we're in deep space, there's no other gravitational forces that would happen to be pulling towards the center of the circle. The only force that could be acting is the force from the floor on the person. And so in this case, the force from the floor on the person, or I think in this example I said, let's imagine the person's standing on a scale. What does the scale read? So I'm going to let you go with this one. In this case, this rather large spaceship, its radius is 75 meters. And typically these things tend to be big. You don't want to be in a small circle and just be on a little hamster wheel. You'd rather have it be more or less flat looking to you. We're asked, first of all, an old-fashioned question for us, or old-time question for us. What's the weight of this person on Earth? 85-kilogram person. That's just mg. Then we need to figure out what their speed is as they're rotating around the center. That's the distance over time trick. Then we're going to use F net equals ma components to figure out what that scale force would have to be so that they're accelerating towards the center with the correct acceleration that they need. That's v squared over r. So try at least A through C. D, the first time you do it might be a little bit trickier, but I think A through C are kind of similar to the one we just looked at, although maybe this is a more confusing context because if you haven't thought about this kind of way of simulating gravity, this person, as they go around, just feels the floor pushing up on them, or the scale that they're standing on. So they feel completely normal if it's spinning at the right rate. If it's not spinning fast enough, they feel too light. If it's spinning too fast, they feel super heavy. So you want to have it spinning close to the correct rate to simulate Earth's gravitational kind of pull, even though there's no gravity anywhere in this problem. You mean standing on, when you say the other side, you mean with their feet right there? Well, let me try to put it into words that you probably are more familiar with that correspond to a non-inertial reference frame. This person who's in there, their point of view is going to be a non-inertial reference frame because they're accelerating as they go around. And so they're going to, see forces going. Now, if you're on a merry-go-round on a playground, perhaps you're familiar with the fact that you feel thrown to the outside, right? If it's spinning really fast, you got to hang on, and it feels like you're being thrown to the outside. You have to pull yourself towards the center to keep from flying to the outside, right? So it's the same way here. You could imagine this person feeling like they're thrown to the outside, and there's nothing pulling down like there is in the case of a playground merry-go-round. Instead, they're thrown to the outside, so they have to kind of stand on the outside with their head towards the center to keep them turning. Yes. You know, I could imagine that I put a little figurine inside this cup standing on the bottom, and ignore the gravity that's here inside the room. So I've got a little figurine standing with its head towards up right now, and then I swing it around like that, right? And if I swing it fast enough, and they didn't fall over from the vibration, you could imagine those feet just going around like this, standing on the outside of the circle. Well, what's the other force? When you say the ground, you mean this part of the spaceship? Right. Yeah. And what's the other force you were talking about? Yeah, so the centripetal force isn't a force at all. The centripetal, in fact, I made a big deal in the video, or at least I tried to make a big deal about, I don't like the word centripetal force because oftentimes there's more than one force. And the forces that are going to cause uniform circular motion, in other words, why isn't this person going in a straight line? Why are they going in a circle? Well, it's because the floor is pushing on them and keeping them turning. There's no other force beyond the forces we already understand. So the forces we're going to look at that cause this circular motion are the same old forces that we already know about. There's no additional thing called the centripetal force. Sometimes people use centripetal force as just the sum of all forces that happen to have components that point towards the center of the circle as you're going around. But they're the same old forces we always knew. We don't have to add in something new. There are no new forces we learned about in the context of this chapter. This is just an old contact force of two surfaces pushing on each other. Yes. So, well, it's not relevant, but if I were to say, instead of the floor causing them to curve in a circle, if I, you know, this looks kind of cruel, but I've got the string here attached to someone's head, right? And that person's going around in a circle, then it would be pulling from this side. So we could glue this person's head to the ceiling and they would still be going in a circle, but we wouldn't want to live like that on a ship. So that would be more like the string pulling, but in this case, pulling upward is the same thing as pushing from the bottom in terms of the effect. They're both pushing in that direction. It's just how I would like to be in this ship and feel like the pressure under my feet, not from something pulling on top of my head. Okay, so let's come together. I forgot to put my numbers up there, but in this case, any questions about A, when you calculate M times little g times 9.8, you get 833 newtons. So the weight of this person, just for reference, is 833 newtons. And what we want to do is figure out if this person's standing on a scale right here, what does the scale read? And if it's more than 833 newtons, that person's going to feel too heavy, like they're really being pulled down as if they're on the surface of Jupiter or something like that, and they're more than their normal weight. If it's less than this, then they'll feel too light, and maybe they can jump up really high in the air, assuming there's room for it in the spaceship. So in order to do that, we're going to use this v squared over r, and one of the things that we need to calculate first is the speed at which this person is moving relative to the center. We're sort of riding along with the spaceship and looking at it. So how fast is the person moving with respect to the center? And we use distance over time. We can do that because the person is not speeding up or slowing down. So any distance, as long as I use the corresponding time. And in this case, we're given an RPM value. So the convenient amount of time I'm going to use is what happens in a minute or 60 seconds. And the question is, how far do they travel? Well, if it's going at 5 RPM, that's 5 2 pi r's. And r in this case is, what was it, 75 meters? I'm going to assume the width of the tube is negligible compared to that 75 meters. You know, persons, it might be 2 meters tall for the person, a little bit less than 2 meters. So that number in part B is 39.3 meters per second. The only reason I care about that is because I want to use it in the v squared over r formula, because we've got uniform circular motion. So in order to answer C, what does the scale read? That's a force that's on this person. Seems like I want to do a free body diagram for that person. I could do the free body diagram at any position as they're going around, but I've already got the person drawn down here. So let me just draw a little blob sort of adjacent to there. This is an 85 kilogram person, so I'm going to, as I usually do, write the mass on the blob that represents the person so I can remember what the mass is, to use an F equals ma. And then the only force, just like in the one we just looked at on the slides, the only force that's acting on this person is the scale force. And if you look around, I mean, we're far in deep space, far from any significant gravitational bodies. We'll find out later in this chapter that everything that has mass pulls on everything else. But, you know, the attraction of my body to this, tripod here is just completely negligible compared to all the other forces that are happening on the surface of the Earth. You need something about the size of the Earth before you start getting substantial gravitational forces. So we're far from all big bodies. There are no gravitational forces. The only one is this contact force. It seems like this person would have kept going straight. Something must be pushing in that direction to cause their path to curve over in that direction. And that's the scale force. And I don't see any other forces that are acting on the person. So that's my free body diagram, step one. Step two is I need axes. I know the person is accelerating in that direction. So our rule of thumb is always take one of your axes pointing in the direction of the known acceleration. So I'm going to take plus x to be toward the center of the circle. And then let's do the sum of the force x components equals max for that free body diagram. Looks pretty simple compared to the stuff we were doing back in chapter 4, but they'll get more complicated. The only force, well, let's see, the only one is the unknown F scale. I'm hoping to solve for that. It comes in with a plus sign because it's pointing in the plus x direction. And that's it for the sum of the force x components. That's equal to the mass of the object in the free body diagram times the acceleration. And since we're in uniform circular motion, I know the acceleration points in that direction, and we already know the length of this vector. Well, we know how to calculate it. It's v squared over r. And we know the v, we know the r. So ax is v squared over r, and we've got our v is 39.3. We got to square it and divide by r. R was 75 meters here. So when you put all that stuff in, I get 1748 newtons. We're comparing that to, this person would feel normal if the scale registered 833 newtons. It's registering substantially more than that, about double that amount. So therefore, this person is going to feel heavier than they do on Earth. In other words, the spaceship's rotating too fast. And in D, we're asked, well, what should the rotation rate be? First, maybe, what should the speed of the person be? That's a little bit easier to solve for. And then we're going to try to convert that into an RPM value, right? Because the faster you're going, the more revolutions you're going to do in a minute. So it seems like if we use that distance over time trick, we might be okay. Any questions on A through C? There's no weight force because right here I have a weight force because this huge Earth is underneath me, pulling on me with gravity. Out there, we've just got this puny spaceship, and even though compared to the person, the spaceship is big, it's really small compared to Earth. So the person is very, very slightly attracted to the spaceship, but you wouldn't notice that ever. In other words, if you go outside of this spaceship on a spacewalk, even if you just push with a little bit, you would just fly away. There's not enough attraction to you to the spaceship to keep you from just flying away, even if you gave yourself a tiny push. You need a huge body to give you the kind of acceleration we have here on the surface of the Earth. And the Earth is huge. Okay. So in this case, we know what we want. So I'm going to do part D now. We want F scale to be equal to 833 newtons, right? That's what I wanted this to come out. So what I'm going to do is say, I'm going to do something like what we had up here, but instead of finding out what F scale is because I knew V, I'm going to say, I know what F scale is, and I want to find out what V should be. And then once I figured out what V is, I can use the distance over time trick to turn that into an RPM value. So let's just repeat this over here. F net X is equal to M times V squared, that's my unknown V, it's a different V than we found before because it has to rotate more slowly, divided by R. So if I look at that equation right here and solve for V, that tells me that, move over here, that tells me that V that we need is 27.11 meters per second. That's a little bit slower. That's what we were expecting. The person's too heavy. They feel too heavy, and therefore it shouldn't be rotating that fast. So they've got to go a little bit slower, 27.11 meters per second. So that's part of the answer. And then we're supposed, oh, it's actually not part of the answer. We're supposed to convert this into a rotation rate. So anybody have an idea of how I would go about saying, what RPM value would this correspond to? Jeremy? Right, I'm gonna basically write down this and fill out the right-hand side, right? So speed is equal to distance divided by time. If we're interested in an RPM value, the time is the M is minutes, so we want to choose 60 seconds for the denominator. And the question is, how far do they move? Well, I don't know how far they move, so I'm going to put in a little placeholder here. I'm going to say, what we did before, we were moving at 5 RPM, rotating at 5 RPM. The 5 went right there. Here I've got an unknown number of RPMs. I don't have a good variable name for this, but I'm just going to put number of RPMs as my variable that I'm going to try to solve for, times 2 pi r. 2 pi times 75 meters. Okay? So there's an equation. This equals this. Okay? Look at that equation. The only unknown in it is the number of RPMs. So when I solve for the number of RPMs, I get 3.45 RPMs. 3.45 revolutions per minute. So, and that makes sense. Before we were going at 5, that was too fast. We had to slow it down a little bit to get the normal weight. Okay, questions on that example? Now, even though this is a very unfamiliar context, and by the way, I highly recommend, if you've never seen 2001: A Space Odyssey is a good film, a little bit dated now, but Stanley Kubrick's a great film director. Even though this is an unfamiliar context, it's a simple application because there's only one force acting on the object as it moves around. And we're going to start to loosen that and put more and more forces in. The next two problems, which I said we're going to do problems 1 through 3 here, the next two problems are kind of still simple, because there's only one force that has a component that points along the direction to the center of the circle that the object is moving on. But it's a little bit maybe more confusing than this one still. So in problem 2, we've got, an old-fashioned record player or turntable kind of thing oriented horizontally, so it's spinning around. We put a mass on it. The mass is at a distance of 30 centimeters from the center of rotation. We're given the mass, 0.12 kilograms, and we're given the coefficients of static and kinetic friction. Of course, if there were no friction between the object and the turntable, it wouldn't even move with the turntable. It would just sort of sit there and slide on it, or if it started moving with it, it would slide off the turntable and fall to the outside. So we need friction. If it's sticking on the turntable and not sliding with respect to the turntable, it is static friction we're concerned with, right? Until it starts sliding. So we turn on the turntable, happens to be set at 26 RPM, and we sort of watch this thing. We say, hey, it doesn't slip. Just happened to be turned on at 26 RPM, and it's not slipping. The first question is, how big is the friction force that's acting on this? And should I use the formula mu static times the normal force to calculate it in this case? No, several of you are shaking your heads no, because there's no indication in the wording that says this thing is about to slip. There are lots of speeds it could go around with and not slip. I know if I turn up the speed fast enough, it would start to slip, but here's just some random speed that it's on. It's not slipping, we just observed it. So there's no reason to believe that it's barely hanging on and about to slip. So instead, what we did before when we were trying to calculate unknown friction forces like this is just use a free body diagram and use that unknown friction force as your variable that you're trying to solve for and figure out what it needs to be. This object happens to be going in a circle, so we know what its acceleration is, right? It accelerates towards the center of the circle with v squared over r magnitude. So see if you can put that together to answer part A, and then in part B, then we're asked about if we slowly turn up the speed, at what rotation rate does it slip? That has to do with that mu static times the normal force. Okay, let's do this together. I see several of you sort of looking through your notes and maybe looking a little bit stalled out on the problem. And you're going to, again, start to see that we do the same things in all these problems, but you need to see it enough times to sort of get that rhythm of the problem. So in this case, there's an object going in a circle. I've drawn it a little bit edge on like it was in the figure in the worksheet. And what I'm going to do is, it's always, if you're drawing something kind of edge on when it's going in a circle, it's always convenient, we'll find out, to draw it when it's sort of at an extreme distance to the right or to the left, if you're looking at kind of an edge on picture. So here I've drawn this object when it's as far right from this point of view as it's ever going to get. And I put the relevant information on there. And what I'm going to do is just draw a free body diagram for this object. It's 0.12 kilograms. We're here at the surface of Earth, so hopefully I'm not giving anything away that there is a weight force in this case. It's 0.12 times 9.8 mg. And there's got to be a normal force, right? Otherwise it would be falling straight through the turntable. So here I'll label this as Fn. And if those were the only two forces, there would be nothing to keep it from, those two are going to exactly balance out. And so the net force would be 0. It would keep going in a straight line. It wouldn't go in a circle. In order to cause it to deviate and start turning, if I were looking down, it might start turning a little bit to the left. We need a third force, and that force is going to be the static friction force. So I'll write that as Fs, and that's what we're after in part A. So let's write down, well, I guess I didn't put any axes on here, but at this instant, the acceleration of that object is toward the center of the circle. It's in that direction. So I'm going to choose one of my axes, maybe we'll call it plus x, toward the center of the circle. And let's take plus y, maybe a straight up from the surface of Earth. Plus z might point in the direction that its velocity vector is. Its velocity is actually in a third direction that's hard to draw in this diagram. Yeah? Well, because I'm imagining this thing is spinning around on the turntable, but it's not sliding with respect to, if it's wood or vinyl or whatever it's sitting on, it's not sliding on it, it's sort of stuck to it. It may as well have been glued on there. It's not slipping. So once it starts to move relative to that surface, even though it's moving, that's not what determines static or kinetic. It depends on if it's moving relative to the surface it's sitting on. And so I tried to write it like that was the case, that it's not moving. Okay, so I'm going to do, again, because I know something about the x direction, or I want to know something about the x direction, let's use the x components of sum of the force x components equals max. 0x component, that's kind of nice. So, even though there's a few more forces, it's not a whole lot more complicated than the one we just did. Fs comes in with a plus sign over here because it's pointing in the direction of my positive x-axis. Okay, and that's equal to the mass of the thing in the free body diagram times the resulting acceleration x component, and we know this is all in the x direction, and its length is v squared over r. So I've got to figure out v squared over r, and in this case, r is always the radius of the circle that the object is moving on. So in this case, r is 30 centimeters or 0.3 meters. Well, I thought it was 30 centimeters, so that's 0.3. 0.03 would be 3 centimeters. So I only need to figure out v, and that's the same trick we did before, right? So to figure out v, I do the distance it travels divided by the time. We know an RPM value, 26. So in 60 seconds, it goes 26 complete revolutions. Each revolution is a distance of 2 pi r. And when you calculate that, you get 1.27 meters per second. Okay. Where am I looking here? Oh, yeah, I'm looking at the wrong part. Yes. So, no, I'm sorry, it's not 1.27. looking at the wrong part. It's 0.817 meters per second when you calculate that. Okay, so I can put that in here. Let me just do that by erasure. 0.817, that needs to be squared. That's my v squared over r. M times a, m times v squared over r. And when you calculate that, you know, you get a sort of uninteresting number, 0.267 newtons. That's the static friction force. It's not at the breaking point. You could calculate what mu static times the normal force is, and you would find that I actually did check it to make sure I didn't make a fool of myself and have this actually turn out to be bigger, since I gave you what mu static was. You'll find out that the maximum static friction force is larger than this, so it's not about to slip. Questions on A. In B, we're supposed to consider when it is about to slip. So we start it from rest and we turn up that rotational rate slowly, slowly, slowly. So at every instant, it's essentially in uniform circular motion. It's not speeding up a whole lot. We're just slowly bumping it up. And then at some rotational speed, the mass will begin to slide. You probably have that intuition. If you spin something too fast, the friction is not going to be enough and it's going to slide off. What is the speed that it has when that happens? And let's convert that to an RPM value just to get practice going back and forth between them. So the only difference in the free body diagram for B is that we're talking about the case where I'm interested in the speed it has when it's just about to slip. And when it's just about to slip, the only thing that changes in the free body diagram is this is the maximum static friction force. And that's the case where it's appropriate to use mu static times the normal force. So I'm going to start exactly the same way, just with my modified free body diagram. Sum of the force x components equals max. 0, 0. This is the only one with a non-zero x component. And since it's the maximum, I use mu static, looking at my numbers, that's 0.55, times the normal force. And in this case, I could use the sum of the force y components equals may, where ay is 0, and then I would find out that the normal force balances out the weight force, but maybe you have the intuition because these are the only two forces with components along the y direction. They've got to balance out along the y direction. And so I can write down the normal force right away as it balances out the weight force. So its magnitude is 0.12 times 9.8. So this is mu static times the normal force. That's static coefficient, static friction maximum force magnitude. That's the only one that has a non-zero x component, and that's equal to the mass in the free body diagram times the resulting acceleration, and it's going in a circle. We're imagining, remember, that it's not slipping yet, it's just about to slip, but it's still stuck to it, so it's going in a circle, it's not sliding off that circle. And its acceleration is going to be v squared over r, and r is still, if it's barely hanging on, 0.3 meters. So there's an equation where I can solve for v, and this is where I get v equals 1.27 meters per second. Okay, so when it's just about to slip, that's how fast it will be traveling, you know, relative to Earth, for example, or relative to the point at the center of the turntable. And then we want to convert that to an RPM value that was also asked for here. So we're going to set this equal to distance over time. The convenient amount of time to choose is a minute if we want RPMs, revolutions per minute. You know, sometimes people, if you want to make it look more like units rather than abbreviation, you could write 26 rev per min or something like that to make it look more like a regular unit. But people tend to write RPM. So that would be an unknown number of RPMs, or RPM value, I'm just going to put that in parentheses, times 2 pi r. Okay, and there's an equation where the only unknown is the number of RPMs, and I get 40.5. .5 revolutions per minute. How about that? Any questions on that? Okay, so you're seeing the things we're going to have to do a lot, figuring out what a speed is given an RPM value, because that's a very common phrasing. Identifying the circle that the thing is moving on. In this case, that wasn't too hard, figuring out the radius of it. We'll find out in more complicated situations. You actually have to think about it. What is the circle it's moving on? What's the radius of that circle? It might not be given in the problem. And then put the object at a certain location, draw a free body diagram at that location, and aim your x-axis toward the center of the circle, because if it's in uniform circular motion, that's the direction it's accelerating. All right, I'm going to give you some time to work on problem 3. You know, in physics textbooks, they always call this ride the barrel of fun. Now, I have seen similar ones, but maybe one that's not quite as exciting as this, but maybe they do have this at certain carnivals or amusement parks where it spins you in a circle. I've certainly seen that. And then they always say in the physics textbooks that the floor falls away from your feet. Does that happen at those carnival rides? Yeah, okay. Maybe I've never been on that exact one before, but I certainly have seen something like it. And the question is, why don't you fall? Your Earth's still pulling down on you. Why don't you fall? So try to answer parts A and B for that one. Then we'll go on and look at some other sort of more complicated force situations where things are still moving in a circle. We actually don't, so you can just put an unknown m in there, and you kind of got to hold your breath, and it does cancel out in the end. If this were an exam problem again, I would probably give you a mass, and you could just put it in, and you'd feel more comfortable with it. But it does cancel out in the end, which is good because you don't want the speed you have to go at to be different for little kids and large adults. So it's good that the rotational rate that it has to go to keep people from slipping is about the same. Of course, it depends to some degree the clothes they're wearing and stuff like that, but we don't want it to be drastically different for little kids. Okay, let's come together. Most of you are working on part B, which is the substantial part of it, but it's crucial that you have a good free body diagram and we show all the forces that are acting. Of course, this person's near the surface of Earth, so that we've got a weight force going down, m times little g. I don't know what m is in this problem, so I'm just going to have to leave the m in there, and as I said, I'm hoping it cancels out, and it will. What other forces are acting? Well, it seems like their back is thrown against the wall, so there certainly is a normal force from the wall. I'm just going to label that as Fn. Now, if those were the only two forces, the net force would be sort of down in that direction, and they would go shooting in that. It would be sort of strange. They need to be accelerating in that direction. We need the net acceleration to be in that direction. So therefore, the net force has to be in that direction. Right now, it's down like that. There's an upward force. What is the upward force that's keeping you from slipping? Friction, and hopefully static friction. Otherwise, you're actually losing out and sliding down. So we're hoping that this is static friction force. And we'll see in part B that we're going to want to use the maximum static friction force to answer it. So that static friction force is the force that keeps you from falling. As always, at this instant that I've drawn it, where the person is most to the right in the diagram, at that instant, the acceleration is to the left toward the center of the circle from that person's position. And therefore, again, I'm motivated to take one of my axes, I usually call that x, toward the center of the circle, and I could choose a perpendicular one. Once again, this is kind of a 3D problem in the sense that the person at this instant maybe is moving straight into the board, so I wouldn't be able to draw their velocity vector very easily in this diagram, but at least I can draw all the forces that seem to be acting. Okay, so that's B. Sorry, that's part A, and then what we want to do is start B. B is, what is the smallest speed that the rider could be moving with and just barely avoid sliding downward? In other words, well, if it's not moving at all, you're clearly going to slide down, right? There's nothing holding you up. The faster it goes around, the bigger the normal force. The bigger the normal force, the bigger the friction force, right? Or the bigger the, at least, maximum static friction force. So we want to see how those relate. So I'm going to, well, since we're interested in a rotational speed, the rotational speed is going to come into the v, in the v squared over r. And that's going to come from the sum of the force x components equals max, right? A is in this direction. This vector has length v squared over r because this person's in uniform circular motion. So the A is going to come into the sum of the force x component equation. Let's just go for it and write down that first. Sum of the force x components equals max. And it's kind of nice. There's only one force with a non-zero x component. That's the normal force. And that's equal to the mass of the person. I just called that capital M here. I don't really know what that is. Times AX, and AX is going to be V squared over R. I do know what R is, 2.12 meters. And our goal was really to figure out what speed this was. But I've got all kinds of problems. I still have an unknown M in there, and I have an unknown normal force. And since I don't know where to go from here, I'm just going to hope that if I use the y component, F net y equals may, that somehow helps. So let's leave some blank space down here and switch over now to the sum of the force y components equals may. Let's see. 0 y component for the normal force. This one comes in with a plus and this one with a minus. And I should say in part B, we're interested in when we're at that slowest speed, friction is just going to be barely holding on. So that static friction force really should be the maximum one. That wasn't clear in part A, but when we go to part B, if we're slowing the speed down as much as possible, friction's barely going to be hanging on. So it's going to be just about to let go. And so that tells me that the, well, let's see. The static friction force maximum minus mg is equal to 0. let's just write that out a little bit more. The maximum static friction force is, I didn't write down my coefficients here, but the coefficient of static friction given in B is 0.4. So this would be mu static times the normal force. Again, I don't know the normal force, so I got a lot of things I don't know here. So that's equal to 0. Part of the problem was I didn't know what the normal force is. So what I'm going to do is just solve for the normal force over here. Put the mg over there with a plus sign, then divide by 0.4. And that's going to tell me that in some weird way, the normal force is related to the weight force in this way. And now let's substitute that in the other equation, and we'll see that everything works out fine. The normal force is the same thing as mg over 0.4. And that's equal to m times v squared over 2.12. And now, thankfully, that m cancels out, because I didn't know what m was. Although, if I would have given an m value, you would have just put it in your calculator, and it would have been fine. It would have canceled out anyway. And therefore, v is equal to the square root of little g, that's 9.8, times 2.12, divided by 0.4. All of that under the square root. When you calculate that, you get 7.2 meters per second. And I can go through the same process to get that to an RPM value. I think, yeah, convert the speed to an RPM, I would say. That's equal to distance over time. The time is 60 if I want to use RPM. My unknown RPM value, that's my unknown here, times 2 pi r. Okay, and if you look at that equation and solve for the number of RPMs, you get, according to me, 32.5 RPM. Good enough on those. Those are the ones I considered sort of more straightforward versions of the problems that we're looking at now. They're going to get a little bit more tricky, because the thing that was straightforward about this is there was really only one force that pointed along the direction to the center of the circle, and the other ones were perpendicular. I'm not claiming these are totally easy problems, but they're of the easier variety. If you watch the video and look through the description of the Ferris wheel problem, you know that they can get a little bit more tricky. Other questions before we move on? Okay, let me go back to sharing the screen here. I guess I threw in a couple of reading response questions. Is centripetal acceleration only for constant circular motion with a string force, or does this term apply also to constant circular motion with other forces? Well, we've seen other examples, so yes. We call it centripetal acceleration. It is just the acceleration when something's going, of that object, when it's going in uniform circular motion. So we've seen a scale force in our spaceship. We've seen a normal force from a cylindrical surface, and so on. So it just has generically to do with anything going in uniform circular motion. How does drawing axes work for a circle? I get the vectors of velocity and acceleration will be straight, but only for that instant. If the point keeps moving, it will no longer be on the original axes that you've created. That's true. What we do is just imagine the object is at one instant in time at one point on the circle. And it's usually most convenient to draw it when it's at the extreme right or extreme left in your picture. And we draw axes at that instant that are toward the center of the circle and maybe in perpendicular directions. So in this case, there was one perpendicular direction. Third one, if an object has significant spin on it, would this affect its centripetal acceleration by much? So if we have, oh, here it is. Here's an object. This is my closest thing I could find to a yo-yo, a wooden disc. But if I throw this up and spin it, it's spinning. I wouldn't say that there's just one centripetal acceleration of this object. There are lots of different points, little bits of wood that are moving on small circles and big circles. Some of them are going slowly and some of them are going more quickly if they're closer to the outer edge. So there's different centripetal accelerations for bits of wood all the way as you go from the center to the outside, right? V is changing and R obviously is changing. And so for a rigid object like this, there's more than one centripetal acceleration. You have to be clear about what point on the disk that we're calculating the acceleration. It doesn't have to be a piece of mass, but you know, as long as you've got a point and you know where it's moving, it's got a velocity, and that velocity vector is changing, and so there is some well-defined acceleration magnitude. Okay, so at this point in the video that you watched, I started saying, you know, there might be more than one force responsible for causing the uniform circular motion. In the example of the barrel of fun, you could still say, you know, these two, the upward friction force and the downward weight force canceled out in some sense. So the only one that's really causing the uniform circular motion is that one that points toward the center. But we're now going to look at other ones where there are multiple forces that sort of have components that are toward the center of the circle. We asked earlier about the centripetal force, and I made a big deal in the video that I just really don't like that term, and most physics professors don't like it, but it somehow is in the popular lexicon, and it does appear in some physics textbooks. But it's bad because when people say the centripetal force, what they usually mean is the MA side of F net equals MA, right? The forces belong on this side. When I write down this side, well, yeah, it's related to a bunch of forces, but this isn't a force. This tells me about the acceleration that results from the force. Sorry, I'm gesturing to the board, but yet this, you know, this is, all the forces belong on this side. This is about the acceleration that results from the force. I don't want to call this side a force, because then I might be tempted to put an extra force on this side. So when you think of mv squared over r, that's not a force. It doesn't belong over here. That's just your MA side of F net equals MA. And it's not a new force. We don't have any new forces associated with uniform circular motion. We're using the same old kinds of forces that we did before. So that's misleading because first of all, there might be more than one force, and we're suggesting that there's one force called the centripetal force. We're going to see an example where there's more than one force, but fundamentally, you're mistaking the MA side of F equals MA for a force. All the forces belong on the sum of the force side. Okay, so the next example that we saw in the video involved a conical pendulum. Where's my mass here? Conical pendulum, you know, a regular standard pendulum. People might call it a simple pendulum. I should show on here again. Simple pendulum goes like this. Conical pendulum is just getting that thing going in a circle. So if you watch the mass is traveling in a circle and its speed isn't changing as time goes on. So that's an example of uniform circular motion. And let's just flip through the solution there, and then we'll do some similar ones. I didn't want to exactly repeat that in class. So here were some specifics. We were given the mass of this object, the length of the string, and the angle which the string made with the vertical direction that went straight down from the point at which I'm holding the string to the center of the circle. And we're asked in this problem, what is the acceleration magnitude? Well, I know the acceleration is pointing towards the center of the circle. A mistake might be to think, oh, because it's being pulled in this direction by the string, it's accelerating along the direction of the string. No, it's in uniform circular motion. Its acceleration always points toward the center of the circle. So A is in that direction. And that means the net force must be in that direction. Let me draw a free body diagram for this object, again, adjacent to it. So draw the same blob down there. And there are two forces acting on it. The Earth is straight below, so I have mg going down, but then I've also got the tension force. And when I add those two forces together, use the parallelogram addition rule, you should get a force that points directly to the right. And I tried to draw them in a way where it looked like that would result there. So the net force better be in that direction because we know the acceleration's got to be in that direction. If it's not in that direction, it wouldn't be traveling on a circle at a constant speed. Okay, so let's, in order to find A, I'm going to try to do F net x equals max because that's going to be the magnitude of the acceleration that's along the x direction if I choose as normal x towards the center of the circle. So that's what I'm going to do in this case. Let's fill in F net equals ma. The weight force has 0 x component in my coordinate system. So it's only the tension. I need to figure out its x component. That looks like t times the sine of 35. That's the only non-zero x component. The mass is 2, and this is the unknown a. Unfortunately, I put a brace under it because we don't know what t is. We weren't given that in this problem. So let's just hold on to that, put half a box around to it, and we'll come back to it later. And my only other thing I have to work with is F net y equals may. And when I do that, that of course is going to involve this component of t, which comes in with a plus sign, and the weight force. So it's going to relate t to the weight force. And when I do that, I can figure out what t is, substitute up there, figure out what the acceleration is. And once I've found that acceleration, that is the centripetal acceleration, or it's just the acceleration the object has at any instant, the magnitude of the acceleration. Once I've got that, I can use that and the associated formula v squared over r to figure out how fast it's going. So the next question I asked was, oh, nobody told me how fast this thing is moving as it's going around in a circle. But apparently it's determined by these 3 numbers that were given there. In fact, you don't even need the 2 kilograms. You'd find it cancels out. So I would just say v squared over r is equal to v squared over, well, again, be careful. A lot of people say, oh, r is just 0.5. It is a distance that was given, but it's not the radius of the circle that it's traveling on. The radius of the circle that it's traveling on looks like this distance here. And I've got to calculate that from the right triangle that I'm making out of the figure right here, right? 0.5 times the sine of 35 times the cosine. That's a mistake in there. Oh, I did. Okay, good. I was hoping. It's been long enough since I made the video that I'm not having deja vu about it anymore. But yes, that should be a sine of 35. I believe, if I remember correctly, I said I thought the number was correct, but just that I had mistakenly put in a cosine when I was clicking on the equation instead of a sine. So that should be 0.5 times the sine of 35 degrees. Hopefully we're all clear on that right triangle stuff now. So that's my r, and I know the result of v squared over r is the magnitude of the acceleration we know, so I can solve for v. That's sort of interesting. Just from that information that's given, the angle and the length of the chord, I can figure out how fast it has to be going in a circle. And if I wanted to, I could convert that to an RPM value. I don't think I did that here. All right. I also noticed that in this case, if someone asked you, well, what's the centripetal force? Your answer might be, oh, we forgot to include the centripetal force. No, we didn't include it because the centripetal force isn't a new kind of force. It's the same. We already know the kinds of forces that are going to cause this circular motion. In this case, we looked at it. There's only a tension and a weight force. There's no new third force that is the centripetal force. But neither of these points in the right direction. It's the sum of the two that points in the correct direction. So again, that's sort of a misleading term, centripetal force. A lot of physics professors don't like that. All right, let's look at problems 4 and 5, continuing with the theme of amusement park rides. You know, it's fun to go in circles at high speeds. So we're looking here at, I'm sure I've been on this at least with my kids, but you know, probably as a kid myself, where you have the chairs that are suspended by chains from a big disc, and the whole thing whirls in a circle, and you kind of get thrown outward at an angle, so your chain is at an angle. So looking at an idealized diagram down below in problem 4, we're imagining that this person is the distance to maybe the average center of the person is 2 meters from the edge of that spinning disc at the top to the center of where the person's mass is 2 meters. They're flung out at an angle of 30 degrees relative to the vertical direction, and that central disc has a diameter of 9 meters. And we want to answer the questions that are on there. First, it's going to be important to find the radius of the circle that the person is moving on, and that's not given in there. But then find the tension in the chain, find the acceleration magnitude, and from that you can get the speed of the rider. So try that one. Sort of similar to the conical pendulum, but maybe a step up from that one in difficulty. You'll see that these problems we're working through here will help you a lot on the homework, because I went through the homework and I sort of tried to pick out some problems that usually there are lots of questions on, and I thought, since we have lots of problem solving time in class this semester, and that's great, let's go through them together, practice working them, and discuss all the subtleties. Anyone having trouble getting started with A? The radius. So the first thing you need to visualize is what is the circle that this person is moving on, and it might, sort of look like this, where, it goes out at an angle on the other side. So we're looking for that radius, and you can break it up into two pieces, right? How far is it from there to there? Plus I've got to add on there. So I've got a right triangle problem. And this looks like it's half of 9 meters, right? 4.5. So break it down like that. Yep. Yeah, I mean, the problem is we don't really know the velocity, and we want to know that speed down at the bottom. So it seems like we can get away with not knowing it for now, at least if you trust that I haven't like ordered the questions in kind of the wrong logical order. So to do it, here's your free body diagram. You've got two directions. One is toward the center of the circle, and another one's perpendicular. What if I do sum of the force components along this direction equals ma? Well, the only unknown one is going to involve the t, because I know everything about this force, right? So I can relate that to t, and it's not accelerating at all along this direction. In other words, its y-coordinate is completely constant as it goes around, so ay is 0. So instead of, so don't use the x, or toward the center of the circle components yet in B. Well, it's not the weight force because you need this component of the tension balances out the weight force. In other words, it's not the tension's going along that direction. I'd need to figure out what its vertical component is. So draw a little right triangle, right, going from the tail to the tip just along y and then just along x. So put some axes on there so you know what x and y mean for you. Yes. So the acceleration is going to come into the ma part of F net equals ma, and we know it's accelerating at the point shown in the diagram. This child is accelerating to the right because that's toward the center of the circle at that instant. So, and that's the point at which you're drawing your free body diagram. If we call that the x direction, which you did, let's do F net x equals max, and that ax is just going to be the a. We want to know that a, because the magnitude of the acceleration is going to be all along the x direction. Okay, some of you are getting, looks like, close to done with this problem, so let's go through it step by step. Maybe you've already done the first parts and you don't have to pay attention to those right now. But R, in this case, this is the circle that the rider plus the seat are going on. They have a mass of 100 kilograms combined. And so I can think of that R as being composed of two parts. One part is half of 9 meters. Right? 9 meters was the diameter. So R is equal to 9 over 2 plus some extra. And that's this side of the right triangle. 2 times the sine of 30 degrees would give that side. And I have 5.5 meters. Okay, that was A. B, we'll clearly need that R for our V squared over R stuff. If we're given the mass of the rider plus the seat, 100 kilograms, find the tension in the chain. We're going to imagine the chain is massless here. That's probably not true, but we'll imagine it is. The tension in the chain. So for this, I need a free body diagram because that's one of the forces that I want. So let's draw how it fits into a free body diagram. I've got a 100 kilogram mass. There's a I'm going to draw it at this instant in time when it's at the leftmost position. So there's a tension going up and to the right at that instant. And if you like, this angle is going to be 30 degrees. It's going to be the same as this angle up there, which was kind of given in the problem. And then there's a weight force. And I think those are the only forces acting on this person. So 100 times 9.8. And, well, I want to know something about T. It seems like I can relate T to the weight force by using some of the vertical components of the forces equals ma. So I need to define some axes. At this instant in time, the acceleration is toward the center of the circle. We're not going to use that yet because I'm interested in vertical, but I'm going to take plus y to be up, perpendicular to the direction towards the center of the circle, and then do the sum of the force y components equals MAY. If you did sum of the force x components equals MAX, your AX would involve a V, and we don't know what V is, so you'd kind of get into trouble there. But in this case, I can clearly see that the y component of T better balance out the weight force because it's not accelerating in the y direction. How would I justify the fact that it's not accelerating in the y direction? It's not moving vertically. So one way to say it is, look, it's what in this coordinate system, its y coordinate is always constant. If you're sitting at the same coordinate, you're not accelerating along that coordinate direction. Or we could say, look, it's in uniform circular motion. Its acceleration is along that direction. That has 0 component along the vertical direction. Either way, it's 0. So I get T cosine 30 degrees minus 100 times 9.8 equals 0. And you can solve that for T, 1132 newtons. Okay, any questions on B? C asks, what's the acceleration magnitude of the rider? Well, the acceleration is pointing towards the center of the circle, so I better use x components now. And it's good that I found that T first. That's going to come in to the x components too. Sorry, this is C. Sum of the force x components equals MAX. The sum of the force x components. This has 0 x component here, so the only one I need is a T times the sine of 30. That comes in with a plus sign. That's the only force on it that has a non-zero x component. That's equal to the mass of the thing in the free body diagram, 100 kilograms, times AX. And AX is, the acceleration is pointing towards the center of the circle, and it has magnitude A, so that's going to be the magnitude of the acceleration. I'm just going to make that my variable here. Plug in my T that I got, and then I can solve for A. And I get A is equal to 5.66 meters per second squared. Okay, and then D, what's the speed of the rider? Well, how would I do that last part? Use V squared over R. I haven't used V squared over R. And in fact, if I had put V squared over R there for A, I could have directly solved for V. But now that I've got A, I could just say, oh, well, that's equal to V squared over R. We already worked hard to find our R, 5.5 meters. And therefore, our V can be gotten by a square root, 5.58 meters per second. All right. Again, I'm hoping you're seeing the similarity. We've got to always identify the circle the thing's moving on. That was easy at the beginning. Now we got to think a little bit. If you don't draw this dashed line, it happened to be drawn in the diagram I grabbed from the web. But if it's not drawn, sometimes it's easy to delude yourself and think, oh, is it going along this circle, or is this the radial direction? No. You have to imagine the person going around and drawing out the circle that they are moving on. All right, let's take it again to the next level. Several of you asked, again, I haven't seen all the reading responses, and that's fine. Glad the internet did eventually get fixed last night. But several of the questions, and it's always a source of confusion. I believe that Giancarlo talks about banked curves, cars driving on banked curves. You ever watch a car race or something like that? Typically, if they're going at high speeds, when they go around a curve, a lot of times those curves will be banked. That's not true in all races, but in some of them, they bank the curves, and that's to allow you to take the curve at a higher speed. So here we have, I tried to draw, show in the diagram there, in a 3D sense, what that banked curve track is. We're going to do a simple case where the track is circular. But instead of being a flat circular track where a car has to go like that, you could imagine the car, just like anything that's going in a circle, from the point of view of a rider in the car, you feel like you're being thrown to the outside of the circle. That's that non-inertial reference frame kind of point of view. You really, from someone looking over the top, you want to keep going straight, and the car is pushing you always from the side, or maybe your seatbelt is pulling you in that direction. But you feel like you're being thrown to the outside, and in this case, if we tilt that track so it tilts a little bit towards the center of the circle, I'm always going to have a normal force, and that normal force will kind of help to push me towards the center of the circle. I know I've got to accelerate in that direction. If the curve is, if it's not banked, the car is going on a flat surface, friction has to provide all of that force towards the center of the circle, and your tires can only hold on so much. But if you bank it like this, your normal force also helps to give part of the force that you need towards the center of the circle, and maybe you don't need to rely on friction so much. And the normal force can just keep getting bigger and bigger. It doesn't have a breaking point. You know, of course, your car can only stand so much pressure down towards the track, but it can be huge, and so this can really help out a lot. A cross section through the track, so if we took a slice through the track over here on the right-hand side, is shown down below, where the car is tilted up on a plane. But it's not going along the direction of the plane from the higher part to the lower part, rather it's coming out of the page at that instant, or maybe into the page. So, a lot of text here. If the car drives very slowly, it would want to slide inward towards the bottom of the incline. What does that mean? Let's try to draw a picture here. I'm just going to draw a very crude car. There's the wheels of the car, right? There's my car on the plane. If it were stopped, say, and there were no friction between the tires and the track, this car would slide down towards the bottom of the inclined plane. So at slow speeds, it's the same thing, right? The car is going slow. It's close to being at rest. It tends to want to slide down in that direction. And that means, why is it not sliding down? Well, because there's a friction force from the road on the tires pushing up in that direction, keeping it from sliding down the plane. If it weren't for the rubber on the tires holding onto the road, or the road holding onto the tires, it would slide down in that direction. Now, in this case, the center of the circle is over here, far away. Maybe this is the center of the circle. I know Himangi can't see, but center of the circle is over there at that instant in time that this car is traveling on. If it's going at the other end of that extremely fast, then we know that it's on a circle of a certain radius. If v in v squared over r is big, if it's going really fast around the track, it's got to have a huge acceleration in the direction I've got drawn right there. And that means the net force has to be huge in this direction, right? In that case, the car, well, it's a little bit more complicated, but you can imagine that if the curve is not banked enough, maybe the curve is not banked at all, if the car is going around on a flat circular road, friction's going to have to push in that direction, and the car is going to want, you know, from the point of view of a passenger, you'd feel like you wanted to be thrown to the outside. And so the car kind of wants to slip up in this direction from the point of view of the passenger in the car. So the friction force from the road on the tires actually has to push down in that direction. When you're going fast, it pushes down and keeps it from sliding out to the edge of the track, the friction force from the road. When it's going slowly, it pushes in the opposite direction, up. Somewhere in between, it seems like there should be a switchover point where it's neither pushing up the plane nor down the plane, but rather has zero friction force. And there is such a speed that you can travel at where you don't have to have any friction force at all. What's providing the force in the direction that it's accelerating at this instant if there's no friction? Yeah, the normal force at least has some component which is toward the center of the circle. If I tilted it just the right amount, you could imagine, okay, I've decided what speed I'm going to go at, so I know how fast, I know the radius of the circle that I'm on, and I know the speed I want to travel at, so that determines v squared over r. That determines the length of this vector. That means there's a certain definite force component I need along this direction. If there's no friction from the tires, if we're trying to do it that way, well, the only other force on the car is the weight force. That's not going to help because it's totally perpendicular to the direction we're talking about. The only other force that can help is this one. And so the idea is, if I tilt the plane more and more and more, a greater component of that normal force points toward the center. If I get just the right angle at that speed, I could have it just be the right amount of force to have the correct amount or the needed amount of centripetal acceleration or acceleration. So what is that speed? In this case, it's phrased this way. I've got a track like this. It's of a given radius, and I want to know at what speed I should go around at so that I don't slide towards the center or go to the outside if I imagine I have frictionless tires. Or if I have tires with friction, I don't need to use the friction. There's none of the friction. The car is not being pulled to the outside or the inside. It's just sort of going along at a happy direction. It's the same as if I had maybe a frictionless circular track that's banked like this, and I had an ice cube that slides on it without friction. If I threw that ice cube around at just the right rate, you know, like a ball rolls around in a roulette wheel, if you threw it too fast, it would slide off the edge of the track. If you didn't push it fast enough, it would start rolling towards the center down the banking. But if you have just the right speed, it doesn't have any friction, but if you hit it just right, it can go without using friction at all around in the circle. We want to do the same thing for the car here. Okay, so what I'm going to do is assume, and I was just planning on doing this problem together because it's usually pretty confusing to people when they see it, but I'm going to imagine, let's draw a free body diagram for the car with the assumption that there's no friction acting. So let's draw the other forces, but I'm going to assume, I'm going to make it so that the friction is 0. So there's still a normal force. There's a weight force. My mass of the car, what did I say, 1,700 kilograms? I just totally pulled that out of my head. I don't really know in kilograms what a car mass is, but I'm sure people who are obsessed with cars would know typically what that might be, but it seemed reasonable. And what forces are on it? Well, those are the only two forces. The track could push on it with friction, but we're assuming there's no friction force that it's pushing on it with. So there's only the weight force and the normal force. So that's my free body diagram, step 1. Step 2 is I should put axes on it. All right, should I tilt the axes with the plane or keep them horizontal and vertical? What do you think here? Hannah? Yes, I always stick to that rule of thumb, which is if you know the direction of your acceleration, and here we're at the right, there's a big circle going over here. The center of the circle is that way. That means the acceleration at this instant in the drawing, as I've done it, is to the left. So that, the acceleration isn't really a part formally of the free body diagram, but sometimes I draw it off to the side because it helps me make some choices. So at this instant, it's accelerating in that direction. We said, if you know the direction of the acceleration, always choose one of your axes along the direction of the acceleration, and then choose the other one perpendicular if I need it. Okay, that's step 2. And we're after V, so where's V going to appear? In the X components or the Y components? Should I do F net X equals MAX or F net Y equals MAY if I want to see a V appear? Because that's what we're asked for. How fast should you drive to make it so that there's no friction force that's needed there? Oh, and I didn't draw the angle. It's 33 degrees. I left that off there. Yes, F net X, because when I do MA, that A is going to be V squared over R along the X direction. So let's just go for it. see if we run into trouble, we can always go back to y. And this looks easy. Again, this force has a 0x component in our chosen coordinate system. I've got to think about the 33 degrees. Notice that as I squeeze this angle down to 0, the normal force would go to the vertical. And so it seems like the angle in between the normal force and the vertical is that 33 degrees. So let me just draw this over here. This angle here is 33 degrees. And I'm going to need that because I'm going to need horizontal and vertical components. So in this case, we want the horizontal component, that's the x component of Fn. So I need Fn times the sine of 33 degrees is equal to the mass of the object in the free body diagram times the acceleration. And we're talking about, that's the direction towards the center of the circle. So it's v squared over r. R was what, 90, 75 maybe? 93. And that looks good, but I don't know Fn, unfortunately. I'm after v. We're almost there, but you know, that's one of my favorite problem solving techniques is saying, well, that wasn't a waste. If I only knew Fn, we'd be done. So let's go over here and try out the y components. Why not? You know, it seems like the normal force would be related to the weight, so maybe we can get it from there. Some of the force y components, that would be Fn cosine 33. That comes in with a plus sign in my coordinate system. And the weight comes in with a minus sign. That's equal to the mass of the thing in the free body diagram. And what's AY? It's 0. Because its y coordinate is constant. Or because A is pointing along our x direction, so it has 0 y component. So I can solve for Fn there. Fn is almost 20,000 newtons. I wrote a lot of places here, but Fn is 19,865 newtons. And then I'm going to plug that over here and get V is equal to 33.0 meters per second. And that's the answer to what's asked in A. If you drive at that speed, constant speed, your car is not trying to speed up or slow down in this direction, so it's not tugging at the road, either pushing it back or pushing forward on the road. But it also doesn't have to tug at the road either down or up, or the road doesn't have to push it up or pull it down with respect to the tires. So you're not relying on static friction at all. You may as well be driving on wet ice where there's no friction to be relied on, and if you hit it just right, you'd keep going around on that track, assuming there was no loss of energy due to air resistance and all that. Okay, that's A. Questions on that? Yes?
Does it really matter which, if you draw your angle on the outside or the weight force?
It does matter. I mean, so in this case, the usual way we would draw this is like this. Now, suppose I had done that. Now you, Anna, were the one who told me to choose my x coordinate horizontal, not tilted, right? So how am I going to, well, first of all, how do I find the x component of this and the y component? I need an angle. It's tilted. I need to know some angle. Do I need an angle down here to find the x and y components of this force? No, I don't. I already know it's all along the negative y direction, and the length of it I know, so the x component is 0. So it doesn't hurt to draw it down there, but I don't need it, and I really do need it up there. So you've got to kind of think, well, any vector that is tilted not all along x or y, I better have an angle next to it. That's one way to think of it. Sam? It's entirely possible that I mess things up. Anybody else agree with me or disagree? You're not getting it. Okay. I didn't bring my, oh no, I did bring my calculator today. Let me just check and see if I see any obvious mistakes and things I've written down here. So everybody agrees with this equation. It's just a matter of plugging those in. So somehow I just flubbed it in my calculator. Fn is 19865 times the sine of 33. Take that result, divide by 1700, and multiply by 93, and then take the square root of that answer. 24.33, is that good? Okay. Thank you. Okay, and then in B, now we're going to push it to the limit. We're saying same parameters for the track, same angle, same radius of track that it's going on. But this person's, they were driving without friction, but now they're going to drive faster and faster. From their point of view, they feel like they're being thrown to the outside. So the car wants to slide up the inclined plane, which is to the outside of the circle. And so that static friction between the tires and the road, why is it static? Well, if it were kinetic friction, the tires would actually be sliding on the road. So with respect to that direction, they're not moving, right? They're coming down and they're not sliding to the side like that. So it's static friction. And that static friction has to push more and more in that direction. Or another way to think of it is, well, look, the weight force is what it is. The normal force was related in a predictable way to the weight force. So that is what it is as long as I keep the same angle on the track. So if this thing starts driving faster and faster, R is the same, but our V squared is getting bigger. So our A is getting bigger. That means I need more force in that direction. The normal force can't help out. It's already predetermined by the weight force and the angle of it. And we're not changing those. Weight force isn't helping out. We've got to have another force beside those two, which is going to start pushing toward the center. And if we have a static friction force pushing in this direction, because it kind of wants to slide up, it pushes down in this direction. At least it's going to have a component along the direction toward the center of the circle. So the question is, if you know that coefficient of static friction, here it's given as 0.55, what's the maximum speed the car could travel around the track and just barely avoid slipping to the outside? And once it starts slipping, it's all over because, you know, it had a big static friction force, and all of a sudden when it starts slipping, remember the coefficient of kinetic friction is always smaller. So then it's not even close to sticking anymore, and you just slide to the outside. So you don't want to go beyond that point. But this is saying, where is that point where you would really start losing control and go off the circular path? And our approach is essentially the same. We just need to add another force to our free body diagram. We need a static friction force, and if we're trying to push it to the maximum, we want that static friction force to be as big as it possibly can be. So that means it's equal to mu static times the normal force. Okay, and our goal is to solve for what V is. And I'm going to do that the same way by using the sum of the force x components equals max, sum of the force y components equals may, and the acceleration is still to the left. I'm not sure why I erased that, but A is still going this way. Okay, since I'm after, you know, when this is maximum, the V is going to be maximum. We'll see that from the x component equation. And the V is going to appear in here, so again, let's go for it. We'll probably have to go over to that one, but let's at least go for it at first. All right, so 0x component, but these two both have non-zero x components. So I need this angle here. This is 33 degrees. And you can think about to yourself, this angle here is 33 degrees, right? As the plane goes down to 0, this would tip up to 0, so it's moving through 33 degrees. Or you could do a proof by going around the diagram. Okay, so both of these vectors here have positive, if this is my positive x, they're both positive x components. Fn times the sine of 33 degrees, that would give me this side right up there. And mu static times Fn, that comes in with a plus sign. Mu static is, I think, 0.55 in this problem, times Fn. And then I need to get this side of the right triangle. That's a cosine of 33 degrees. Okay, that's the sum of the force x components. The third weight force has 0 x components. And that's equal to the mass of the thing in the free body diagram times its acceleration. And I'm going to write that as v squared over r. R was 93, right? So that looks promising, except that I don't know what Fn is. If I could only figure out what Fn is, I'd be good. And then we get Fn, of course, from the sum of the force y components equals MAY. All three forces have non-zero. I'm not going to have enough room to write here, so I'm going to move that back over here. So let's hold on to this. Sum of the force y components equals MAY. We've got a lot of them here. All three of them point along the y to some degree or the other. Fn times the cosine of 33 degrees. That comes in with a plus sign. The other two have negative y components. Minus mu static times Fn times the sine of 33 degrees. There I'm finding this y component of this force, and it's negative. And then this one's purely minus y, minus 1700 times 9.8. Okay, and what's that equal to? On the other side of Newton's second. It's 0 because it's not accelerating along the y direction. It's not moving at all. It's not progressing along the y coordinate. So I could combine these two together. This is Fn times the cosine of 33 minus 0.55 times the sine of 33 degrees, whatever that number is equal to 1700 times 9.8. I just put that on the other side with the 0, and then I can divide out whatever that mess is in parentheses to get Fn. It's not a very interesting number, but I get Fn is 30902 to 5 places of precision. 30902 newtons. And then, of course, I'm going to place that number up here, and that will allow me to calculate V max, the maximum. We assumed this was the maximum static friction force, mu static times the normal force, and therefore this corresponds to the maximum speed over there, and you get V maximum without slipping is 41.2 meters per second. Hopefully that's not affected by, no, I don't think that's affected by my mistake I made on the previous page. That's typically a very confusing, I think there's one homework problem that asks about it, but everybody always asked about it in the reading too. Whew, all right. Any questions on that one? Yes, Jeremy. It could be. I mean, I would say this would be a difficult kind of problem in my mind on an exam. It's not totally undoable. It's a little bit of a mess, more messy algebraically than it is conceptually difficult once you've been through it. But the first time you see it, it's somewhat confusing about how to think about the forces and how this is possible without friction. But all right, let's go back if there's no questions there. There may be some reading response things here, so let's go back to the slides. just one here. I don't understand how friction force can point perpendicular to velocity. Then the direction of the friction force can change directions if the brakes lock. Can you explain this more? So this was something from Giancali, and I have to, I put this in here because I was imagining what was meant when I put it in, and now I'm forgetting. Friction force can point perpendicular to velocity. So that's certainly the case here. If this car is traveling around at a constant speed, if it were trying to speed up, then the tires kind of have to push back on the road in order to push it forward. That means the road is pushing forward on the tires. But if it's going at constant speed, the tires don't have to push on the road at all. They're just sort of rolling over the road at a constant rate. But if it's trying to slide to the outside, the friction force has to push along this direction. So in any case, the velocity maybe here is into the board. The friction force is perpendicular. That's the first part of that. Then the direction of the friction force can change directions if the brake locks. So imagine all of a sudden this car slams on the brakes. Let me unshare that. So the friction force is in this direction, velocity is into the board. All of a sudden, the car locks the brakes up. That means the car is slowing down. It's accelerating in this direction. That means the road is pushing on the tires in this direction. It's no longer static friction because now it's sliding with respect to the road. But that friction force now might be partly down the plane and also partly in this direction, so it's not going to be perpendicular to the velocity. You're just right when you slam on the brakes, you're still going in that direction in this diagram. But now all of a sudden the friction force from the road is trying to slow the car down. If it's going into the board, the friction force would be pushing back in this direction and probably still some down the plane too. And it would probably start sliding to the outside if it were going fast enough. Okay. All right, here was a confusing problem. And normally, every other semester I would have done this in class, but since I wanted to have some problems to work on in the videos, just to sort of show how problem solving goes, we did this here. So this is uniform circular motion. We're imagining a Ferris wheel progressing around at a constant rate. So by definition, this thing is rigid and it's rotating at a certain number of RPM. I did 7 revolutions per minute, and that doesn't sound like very much, but for this large of a Ferris wheel, you would probably be pretty scared as you were rounding the top of this thing, and you would feel like, oh, I'm getting pretty light. Am I going to fly off my seat? And they probably don't go that fast in reality. But in any case, that's not clear at the beginning. It sounds like 7 RPMs is not that much. We're given the mass of a rider here, and the radius of the Ferris wheel is 15 meters. I can't see that in my screen share here, but it's written up at the top. What's the rider's real weight? That just means mg. We're going to use that for comparison. So going through this problem, mg is 735 newtons. If you're sitting on a scale and the scale reads something different than that, you're going to feel kind of funny, either too heavy or too light. So we're going to use that for comparison. What's the rider's speed? Oh, that's just the distance over time trick. If you're going at 7 RPMs, that's 7 2 pi r's in 60 seconds. So that ends up being 11 meters per second. That's nothing new to us. Let's analyze. So we're imagining there's a rider. The rider is sitting in a seat on a scale, and their entire body weight is on the scale. So in other words, their feet aren't on the ground. They're sitting completely on the scale with their feet off the ground. And we're going to imagine that, just like it's drawn here, the seat that the person's sitting on always stays horizontal. In other words, it doesn't rock to one side or the other or anything like that as it goes around, just as make things a little bit easier. Draw a free body diagram for the rider at position A. We're going to imagine they're sitting on a scale. So one of the forces on them is going to be the scale force, and we want to figure out what the scale force is. What will the scale read at A? Well, here's my free body diagram. Of course, we're near the surface of Earth, and the weight of the person is a force on that person. They're sitting on a scale, and the scale presumably is holding them up. I don't know what it is, but we're going to solve for that. And the important thing is that at this position down here, I'm in uniform circular motion. The direction of my acceleration, or the rider's acceleration, is toward the center of the circle. So at this point in the motion, acceleration points up. That's going to change as we go to position B and position C. But here it's pointing up. So if I choose, why not, plus y to be along the direction of the acceleration, that's what we always do, and do F net y equals may. When we write that out, on the right-hand side, we have m times v squared over r, because y is the direction along which the centripetal acceleration points. We can solve for F scale. And I don't know if you have this intuition, but as you go around the bottom of something, if you go really fast along the bottom of something, or maybe if you're in your car driving too fast on a country road out in the middle of nowhere in Kentucky, and you go down in a gully and your car really kind of hits the bottom like that, you feel heavy. And it's the same way here. As you round the bottom of this curve, you're going to feel heavier than you normally do. So the scale reads 1340 newtons. And in every respect, you would feel like you would feel on a more massive planet where you had a bigger weight, where little g was bigger than 9.8. So that's a pretty substantial difference, not quite double your weight. So sometimes people call this your apparent weight. If you put a scale under you, whatever that scale reads is what your apparent weight is. And you're going to feel like that's what your weight is. So it's bigger. You feel heavier at the bottom. And in this case, you know, I think I asked in this problem, how big is the friction force on you? You're sitting on a seat. It's a completely flat seat, I'm imagining. But it may be that my body kind of wants to scoot forward and friction has to push back or something like that, right? Hopefully a static friction force. Hopefully I'm not sliding on my seat. But what would that static friction force have to be to keep me on that circular path? And in this case, you know, I had an unknown F scale. I could also put an unknown static friction force, maybe pointing to the right, or if you like, pointing to the left. The seat's horizontal, so it's got to be along the direction of the seat. But in any case, it's the only force pointing along that direction, and the acceleration doesn't point along that direction. And so when I do F net x, I would just get F friction. And when I do ma, I get 0. So it tells me the static friction force has to be 0, if you were worried about it there. Okay. Next, position C at the top. Everything looks the same. The scale, hopefully, unless you're going really fast, the scale's still hopefully pushing up on you, right? You're still sitting on the seat if you haven't lost touch with this Ferris wheel. Your weight's still going down. I'm going to choose plus y as up. The only difference is when I'm at the top of this Ferris wheel, the direction towards the center of the circle is down. And that makes all the difference. When I do F net y equals may, the left-hand side looks exactly like it did before. Now, that doesn't mean F scale is the same, but it's still an unknown that appears over there. The only thing that changes is now A, which is v squared over r. I just pulled the number from before. V squared over r was 8.07 meters per second. AY is negative. I happen to choose plus y is up. We know that when you're at the top, A is down, and so AY better be a negative component. And that makes all the difference, because when I take this negative number and move it over to the right-hand side as a positive number, it's now having something subtract off of it. Got a positive number minus something. And that means the scale is going to read less than 75 times 9.8, which is my true weight that we calculated up here. So in this case, only 130 newtons, substantially less than your true weight. So this is a hair-raising part of the ride. Normally, Ferris wheels aren't that scary when you go over the top, except that, you know, if you're afraid of heights, but not because you feel like you're going to fly off. That would be kind of a exciting Ferris wheel. Same argument gives 0 friction force. What about at point B on the side? There, things change. On the side, The direction towards the center of the circle is left in my diagram, so the acceleration points to the left. Well, if I'm sitting on a horizontal scale, the scale force, if I imagine it being a normal force, just points up. Weight has no choice but to go down. There's got to be a force pointing towards the center of the circle that results in that necessary acceleration to keep me going in a circle. The only force I can see must be a force from the seat. That's the only thing exerting forces on me. It's got to be a friction force, hopefully a static friction force from the seat. Hopefully I'm not sliding on my seat at B. And I can figure out how big that static friction force has to be. So in this case, you can see I'm accelerating to the left. That means my acceleration along this vertical direction is 0, and therefore F scale balances out 75 times 9.8. So my weight, my apparent weight is the same. Those two balance out. That's from doing F net y equals MAY. If I do F net x equals MAX, that tells me how big the friction force has to be. The friction force is the only force with a non-zero x component, and that's equal to m times, this is the result of v squared over r that I calculated before. It's the same everywhere around the circle. So the friction force is substantial there. Hopefully you're wearing a seatbelt too, so you're not totally relying on friction. Okay, so the last problem, it's certainly, I feel like we've been going at this for a while, but let's just finish up with this one. It's not too hard. It's about the same as the level of this. Here I have created a baton kind of thing by taking two 1 kilogram masses and attaching them to a rigid rod. So they're at the edges of the rod. And I'm going to imagine the rod itself is massless. That's just an idealization here. So all the mass is in the 1 kilogram masses on the two sides. I place a pivot at the center of it, and then I spin the thing, and it starts, spinning around like this in a vertical plane. So those masses are going up and down relative to Earth. So we're here at the surface of Earth, and they're spinning around like this. At 42 RPM, so it's like a Ferris wheel, except it's spinning much faster. And we want to consider what the force from the bar is on one of the masses as that mass passes point A, point B, and point C. I said, let's let plus x be to the right in the diagram and plus y be upward. Figure out what the force from the bar x and y components are at those three locations, and you'll find they change as you go around in the same way that the scale reading changed as we went around in this Ferris wheel problem. Sure. Is this one what you want to look at? This was point B. Should we go back to point A, which is at the bottom? Okay, I know I haven't given you nearly enough time to finish all of these, but at least you've started thinking about it. I'm going to rush it a little bit because the hour is late and we've done a lot of work today. So let's just try to compare these three and we'll see they're kind of similar. A lot of the work is going to work out the same way. So I think the first one that's asked about is at the bottom down here. Let's do a free body diagram for this 1 kilogram mass. It's certainly got a weight force going down, 1 times 9.8, right? And then the bar is reaching down. It could be pulling on it, could be pushing on it. Bars actually, a bar isn't like a string. A string can only pull along the direction it's attached, but bars aren't like that. You know, if I've got a bar attached to a mass here, a bar can actually, it can pull on the mass, it can push on it, but it can actually push it in the direction perpendicular to the direction that it's attached to it too. So it's not like string in that way. I'm just going to draw, I don't know how it's pushing on it down here, but there's an unknown y component. I'm just going to separate them out. I'm going to write this as f bar y component, and then there's an unknown f bar x component. And we'll just solve for what those are. The only things that are pulling on this are the earth down below and the bar that's attached to it. So that seems like that should be all there is for the free body diagram. And we're told we're supposed to use these axes. That's what x and y mean. So let's just do sum of the force x components equals max. In this case, what's ax at that position down at the bottom? It's 0 because x is not at all along the direction towards the center of the circle. So when I do f net x, I just get the only contribution is f bar x component. These two have 0 x component. And the right-hand side, you just said, is 0. So that tells me that the bar is not reaching down and trying to push it to the right or push it to the left. There's no x component at the bottom. So it looks like all the interesting stuff must be going on in the y direction. Some of the force y components, that would be f bar y minus 1 times 9.8. I'm just going to write that as 9.8. Plus y is up, so that one's negative. And that's equal to the mass of the thing in the free body diagram. Again, in SI units, that's 1, so I'm just going to leave it out because 1 as well. Put it in. 1 times the acceleration, and in this case, we have to figure out what the speed is. And maybe I won't go through that again, but using the distance over time trick for the RPM value that is given, if you worked it out, I got V equals 2.199 meters per second. So this would be 2.199 squared divided by r. If this is a 1 meter long bar, then the radius is a half a meter. Okay, and that allows me to solve for f bar y. (19.5 newtons). Notice it's bigger than the weight of the mass. The weight of this mass is 1 kilogram times 9.8, so it's 9.8 newtons. The bar has to pull up with 19.5 newtons. Why is that? Because it's accelerating upward, and the upward force has got to win out over the downward force if it's going to be accelerating in that direction. Okay, so that's for the lowest position. The next one is the middle position. And let's just try to alter this for part B. What changes in the free body diagram? Well, nothing really. The weight force is what it is. It always goes down with mg. And these were complete unknowns, and I still want them to be unknowns. I've got to solve for them. They may have different values, but I'm going to put in placeholder variables there. So that's all the same. The only thing that changes is now, in this case, for part B, the acceleration towards the center of the circle is to the left in there. So this isn't the same anymore. The left-hand side is the same, right? F bar x is still the only thing going along the x direction. But now, let's see, if plus x is to the right, A has a negative x component. Okay, so this is equal to the mass of the thing in the free body diagram times v squared over r, because that's the direction toward the center of the circle, and it better come in with a minus sign. And my v was 2.199 squared over 0.5. All right, and that number is 9.8. 9.8 newtons. Notice that, 9.8 looks familiar, and that's not surprising. That's the weight of this 1 kilogram mass, and it's saying when you're going by this point and the bar is going straight over to the right, it's accelerating in this direction. It's not accelerating all along this direction, and that means the force from the bar up has got to exactly balance out the weight. Wait. Yeah, negative 9.8 newtons. But I think the argument I was just making doesn't apply to this. I was going to talk about something in the y direction, but we're talking about the x here. It points to the left. Plus x is positive. We sort of guessed it was in this direction, and often we'll do this. This may be the first time this has come up, but sometimes if you don't know which way a force points, you can just guess. I don't know if it points left or right, the x component. If I guess to the right and then I end up getting a negative number for it, it means I've guessed exactly wrong. So that means it's pointing to the left. That's what that minus sign is interpreted as. So in any case, it's pushing to the left with minus 9.8 newtons. And then this y component equation looks like this. The F net part is the same, but the right-hand side is 0. A is pointing that way, therefore A has 0 y component. And so this is 9.8 newtons. This is a little bit of a coincidence that comes from how fast exactly I chose to spin it at, and I kind of chose something that would make it very close to 9.8, so that it would be, we're going to find out the bar y force at the top is almost 0. Any questions on this one? Okay, last one, just very quickly. At the top, A goes down. What changes here? Again, in the x, we get f bar x is 0 because there's only one x component force, and it's not accelerating at all along that direction at that instant in time. And in the y equation, I get f bar minus 9.8, and on the right-hand side, A has a negative y component, right? So this is equal to the mass of the thing in the free body diagram times the negative y component that has magnitude. The magnitude of the acceleration is 2.199 squared over the radius. And before, at the bottom, this was a plus here. So this positive number got added onto that one and made a bigger force. Here they're subtracting against each other. This is a negative number. When I bring this over here, it'll be positive, so they subtract against each other. I get the small number, 0.129 newtons. In any case, it's changing as it goes around, and that's the end of our time. So we'll continue with this tomorrow. We'll talk about the case of several people talked about the car doing the loop, and the water thing going upside down. So we'll do those tomorrow. And then we'll get into gravity. I probably won't talk about that history of gravity and the history of the conception of the universe, but you'll see that in the videos tonight. So there's a little bit of a sideline on how people used to think about the universe leading up to Newton. Sorry, Himangi, I forgot to switch the video on that last one. I thought I was doing pretty well, but...
Oh, I could still see it. It's okay.
You can see it off to the side, or can you click on it and make it big?
Yeah, that's what I did.
Yeah. Okay, awesome. Great. Okay, I'm going to stop this.
All right.
See you tomorrow.
See ya.